Hey, hi everyone. So David's going to talk today about first and second cohomology groups for BBW Parabolics for classical lead superalgebras.
Thank you very much for the introduction. Hi everyone, thank you for coming. So yeah, I just wanted to spend today talking about, I guess, what I've been working on for the past year or so. And so that's computing these first and second cohomology groups for what are called BBW Parabolics for classical lead superalgebras. So before we get into the main part of the talk, just wanted to give like a brief outline of what we'll be talking about today. So first, I'm going to talk about just a bit of motivation for why this is important. And so that comes from a theorem for computing Lie algebra, ordinary Lie algebra cohomology, Kostant's theorem. And so we'll see what that is, and our goal is essentially to find analog in the superalgebra case. We'll define what a detecting subalgebra is, and we'll use that to find some triangular decomposition for superalgebra. So we're going to write our superalgebra G as some sum n minus direct sum f direct sum n plus. From this, we're going to be essentially trying to look at the cohomology of this subalgebra right here, the n plus. So we'll be trying to figure out this n plus c for I is equal to 1 over 2. To do that, we will construct a Hochschild-Serre spectral sequence. We're going to come up with one for each of the infinite families, and then we'll use that, show it collapses, and we'll use that to essentially just find our computations. So let's just start with the semisimple Lie algebra case. So we're going to let G be a complex semisimple Lie algebra. It's going to have some triangular decomposition, going to be written as n minus plus direct sum t, direct sum n plus, where t is going to be the maximal torus. And I guess we'll say that G is going to be the Lie algebra for some reductively group G. We'll let phi be its irreducible root system. It has a Lie group W. J is any subset of the simple roots, and we'll let P sub j equal L sub j direct sum U sub j. So this is going to be the parabolic subalgebra corresponding to J. So that's just the radical, and that's the LJ is going to be the limiting factor. So what exactly Kostant's theorem tells us is that if we have some semisimple Lie algebra G, J is a subset of the simple roots, and some parabolic subalgebra Pj, then the kth cohomology of Uj with coefficients in the irreducible module with highest weight mu can be written as this direct sum. So it's a direct sum over all the elements W and Wj of length k of this direct sum here, Lj of W dot mu. So Lj is going to be the finite dimensional module corresponding to that limiting factor Lj, and then this W dot mu is just the dot action of the element of the Lie group W on the highest weight. So that's just going to be W applied to mu plus rho minus rho, where rho is the half the sum of the
mu is dominant.
Oh yeah, mu is dominating. Yeah, otherwise that's not true. All right. So this is in fact part of a larger picture. If we look at the parabolic category OJ, where there exists this isomorphism between the x groups, the nth x group of Zj L lambda mu. That's going to be isomorphic to the Hom set over Lj of Lj lambda, comma this cohomology group, which is computed by Kostant's theorem. And it turns out that these x groups can actually be computed via Kausha-Mostly polynomials, but that turns out to be a rather deep result. So let's take a look now at the superalgebra case. So a Lie superalgebra G is defined to be some Z2 graded vector space, G0 direct sum G1, that has some bilinear operation called the super bracket, satisfying the following axioms. So first we have that the bracket of A times B is equal to -1 times -1 to the degree of A times the degree of B times the bracket of BA. So this is essentially just an analog in the super case of anti-commutativity of the Lie bracket. And then we also have the second condition, which is just essentially an analog of the Jacobi identity. So this is just going to be your analog for the super Jacobi identity. So this action, based on when this is going to be positive or negative here, it turns out that it will be, if we look at just the adjoint action, which is just going to take adjoint of x is going to go to the endomorphism x bracket. This is going to make G1 into a G0 module. Equivalently, we can view it as a G0 module. But yeah, this is going to give the odd portion the structure of a G0 module. So let's just look at an example of one of these, probably the simplest example. So just like there's the GLM case for ordinary Lie algebras, for superalgebras, we have this case of GLM. So this is going to be the set of all m plus n by m plus n matrices over C. And we're going to say that the odd elements are, or I'm sorry, the even elements are going to be just all of those matrices of this following block form. So they'll have non-zero entries in the top left and non-zero entries in the bottom right. And then G1 is going to consist of matrices that are essentially the opposite. So matrices with non-zero entries in the top left, I'm sorry, the top right and the bottom left. And then the supercommutator for purely odd and for purely even elements is given by just this definition here. Essentially, we're taking the commutator of two elements, but then we're just including this -1 here to reverse some power based on whether our elements are odd or even. All right. So Cass in a 1977 paper, he essentially classified all of the possible simple Lie superalgebras. So we're going to say that a superalgebra is classical if this corresponding group G0 is connected, reductive, and algebraic. And then G1 is completely reducible as a G0 module via the adjoint action. So then we have a complete list of essentially simple Lie superalgebras given by the following. So we have GLMN. Those are just the ones described above. SLMN, all the ones in GLMN. So that the trace of A minus the trace of B, or trace of D is equal to 0. OSP, which is essentially like an analog of the SO and the SP, the B sub n, the D sub n, the C sub n algebras for the ordinary case is essentially an analog of that in the super case. We have these exceptional algebras. So these are just essentially single algebras D2, 1 alpha, G3, and 4. And additionally, there's a set of, I think Q stands for the queer superalgebras, and P stands for the strange ones. These form a list of all the classical simple Lie superalgebras. Now, they're not all quite simple. Like they do have non-trivial, or some of them do at least, have non-trivial centers, and so they're not purely simple, but at least according to the classification used by both Kujawa and Nakano in their paper, this is sufficient, and this is the classification that they use. Additionally, there are going to be some extra non-classical simple algebras called Kostant type superalgebras. These are a few other infinite families, but we won't be discussing those here. All right. So first, let's just take a look at how the Lie superalgebra cohomology is going to be defined. So this is essentially, again, just an analog of the ordinary Lie algebra cohomology. So if we're going to have G be a Lie superalgebra, we're going to consider the complex whose cochain groups are given as follows. So we have these groups of Cn, Gm, and this is going to be just defined as the Hom set from the super exterior product of G to N, where the super exterior is just given by this direct sum. So it's going to be the sum over all I plus j equals n of lambda, the exterior on I, or the exterior on G0, tensored the symmetric algebra on G1. And then the differentials are going to be given by this formula here, where these coefficients Ti and sigma and Ij are either going to be 0 or 1, depending on what the degrees of the elements omega 0 through omega. So in their 2008 paper, Kujawa and Nakano define what's called a detecting subalgebra. So what they say is that if G is some classical Lie superalgebra, if G admits a stable action, then there's going to be some subalgebra F, which is isomorphic to a direct sum of copies of SL11, so that this restriction map for the relative cohomology of G to the fixed points under N of F is going to end up being an isomorphism. Similarly, if G admits a polar action, then there's going to be some other subalgebra E, which is going to be a direct sum of copies of Q1, so that this restriction map. And so the main, well, actually, let's go down here for a second. The main point of that was that just like in the case of the ordinary Lie algebras, how there's a Chevrolet restriction theorem, which holds for that. There is one similar for superalgebras. So if we have some classical Lie superalgebra with both a stable and a polar action, then we have an inclusion of subalgebras here, E and F and G. And we have this isomorphism of rings here, just like we said above, of the relative cohomology of G into the relative cohomology of F, mapping into the relative cohomology of E. And these are all isomorphic to these fixed points of these symmetric algebras below. Just as an example of what these look like, let's just take a look at the case where G is equal to GL32. Well, this detecting subalgebra is essentially going to be along the main diagonal, so along the maximal torus and the even component. And essentially what we're doing in the odd component is we're just looking at each of the quadrants and then finding its main diagonal. And so this isn't going to be a torus. If we look at the action of FL1 on the algebra, it's not going to be completely reducible, but what we get is, thanks to Grantcharov, Nakano and Wu in 2019, we get a triangular decomposition of our superalgebra G into some subalgebras n minus F and n plus. And then if we look at this direct sum here, this f and this n plus, that's going to be our parabolic subalgebra. And these subalgebras right here, this f direct sum n plus, these are going to be what we're going to call BBW parabolics. So again, as an example, if we look at GL 3.3, well, our detecting subalgebra f is just going to be along the main diagonals in each of the quadrants. We're going to have ones here, here, and here, here, here. And then essentially, and completely analogously to what happens in the ordinary case, our parabolic is just going to be essentially all upper triangular matrices in each of the quadrants. So we're adding elements here, 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 here. Just completing it and making all the upper triangular matrices in each quadrant. And it turns out that that's essentially how the Q3 case is going to look as well. Now, recent work by Y, Nakano, and Wilbert has been done on constructing a category OF. So finding an analogous category to the category O for ordinary cases with this detecting subalgebra F. And they've proven an analog to the X isomorphism that I wrote down at the beginning. What remains a fundamental problem, however, is to compute these HN, these nth cohomologies of n plus with coefficients in finite dimensional modules L lambda, and to determine if there's a constant type formula for OF, just like there was in the ordinary case. So what I'm going to be doing today essentially is computing these cohomology groups for the, I guess for the simplest case, for when our coefficients are just trivial. So when our module is C. So first, let's just recall, if we have an ideal of a superalgebra G, then we have a short exact sequence, 0 maps into I to G mod I to 0. With that short exact sequence, we have a Hochschild-Serre spectral sequence that arises, whose entries are Eij2 is just going to be the ith cohomology of G mod I, comma, the jth cohomology of I mod C. And that's going to converge to the ith plus jth cohomology of G comma C. So what I was able to show is that for each of the infinite families, so the infinite families that I am taking into consideration are GLMN, OSP 2M2N, OSP 2M plus 1 2N, and QN. It turns out that for each of these infinite families, there's going to exist a family of abelian ideals I of each of the subalgebras N, such that this corresponding spectral sequence here collapses on the E2 page. So essentially, how that would be shown is looking at the decomposition of each of these subalgebras into weight spaces. So I would look at the essentially it's a matter of finding just the right weights and then showing that it collapses. So let me just give an example of that for the GL and M case. The ideas that you'll have to use in this case are pretty similar to what you would use in any other. So let's start with GL 3.3, like we had previously. Then the subalgebra N is going to consist of all of these matrices that are strictly upper triangular in each of the quadrants. So if we want to characterize like what all the weights of this are, well, these are going to correspond to weights epsilon 1 minus epsilon 2, epsilon 1 minus epsilon 3, epsilon 2 minus epsilon 3 for this top quadrant, delta 1 minus epsilon 2, delta 1 minus epsilon 3, delta 2 minus epsilon 3 for this bottom quadrant, and so on for the other quadrants as well. So essentially what we're going to do is pick I to be the direct sum of all the weight spaces that have either a negative epsilon 3, or on the right-hand side, this would correspond to weight spaces with a negative delta 3. So what that would mean is picking the elements here, 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 and here. And so that's going to be our I. So I is going to consist of all of these matrices here, whose non-zero entries are in red. All right. So if we look at this subalgebra N, it's going to decompose as a direct sum of its weight spaces under the action of the maximal torus of the larger algebra G. And yeah, here's just the list of the weights again. Now, let's look at these elements of ERIJ. So just like before, E2IJ, we said was this ith cohomology of n mod I, comma, the jth cohomology of I mod C. So it turns out that this is going to be a subquotient, and this is going to follow that it'll be a subquotient for all the higher, for all pages larger than 2 as well. This will be a subquotient of, well, the super cohomology for I, and I. Tensor the, I'm sorry, n mod I star. Tensor the super exterior J on I star. So essentially, we're just looking at this as a subquotient of this tensor product of super exterior. So I guess another thing to note is that if we look at any differential dr, that's going to send just an element of the second page or the right page, I of j to I minus r, comma, j plus 1 minus r. So our dr is going to have 5 degree. Negative r, 1 minus r.
I think it's I.
Yeah, here.
So it should be I plus.
Yeah, you're right. Yeah, it should be I plus r. Thanks for pointing that out. All right. So it has by degree r, comma, 1 minus r. And what's important about our differentials is that they're going to respect the action of the maximal torus. So that means that the differentials dr are going to send weight spaces to weight spaces. So if something has a weight in the IJR, it's going to have the same weight once it's been sent by the action of the differential. So let's look at what the weights of anything in this form must look like. Well, any weight that's going to appear in the super exterior to the ith power here, that's got to be I copies of the weights in n mod I star. Similarly, the weights in the super exterior to the jth power of I star have to be j copies of weights in I star. Now, the way we had defined the ideal j, or I'm sorry, the ideal I, was that all the weights that contained either a copy of epsilon n or of delta n, in this case, epsilon 3 or delta 3, had to appear in the ideal I. Because of this, any weight in here contains j total copies of a weight of the form epsilon n or delta n. So combined, the total number of times that either epsilon n appears or delta n appears added together has to equal j. However, because the differentials for when r is greater than or equal to 2 send ERIJ to something where to ER minus r, comma, j plus 1 minus r, j plus 1 minus r is going to be smaller than j. So any weight in here can only has to have fewer than j copies of epsilon and delta n in total. And because of that, no weight can be sent to a non-zero, or nothing in a weight space can be sent to a non-zero element in its image because no weight exists in both EIJR and EIR, EI minus R comma J plus 1 minus R. So no weight exists in both the image and the element. Because of that, all the differentials have to be 0, and so the spectral sequence is going to collapse when E2H. All right. So that's going to be useful for computing the cohomology, especially the H2 case later on. Right now, though, let's take a look at the H1 cohomology. So we have an analogous result to what we have in the ordinary Lie algebra case. So we're going to define a superderivation from a Lie superalgebra G, which is some G module M, to be a linear map obeying this action, so that phi bracket is just equal to x dot phi of y minus -1 to the raised the product of the degrees of x times phi of x. Similar to what's the case in the ordinary setting, and then an inner superderivation will just be some of these one of these superderivations that's in the form x dot a for some a in our G module. So just how in the case of ordinary Lie algebras, we have that the first cohomology is isomorphic to the set of derivations mod the set of inner derivations. So too we have in the super case, H1 is going to be isomorphic to the set of superderivations mod the set of inner superderivations. So this actually simplifies considerably when we just start looking at M being the trivial module. So when M is the trivial module, this is just going to simplify to us saying that first cohomology is just isomorphic to G mod the derived subalgebra star. So let's look at this. Just some examples of computations with this. Here are probably the two simplest ones, GLNN and QN. So starting with GLNN, all of our elements of n plus are just going to be of the form here. So elements that are upper triangular in each of the quadrants. All right. So our cohomology H1 and C should be isomorphic to n mod the derived subalgebra star. So what are going to be the elements in the derived subalgebra? Well, it's not too hard to show that these are going to end up just being everything that in each quadrant is above the off-main diagonal. So everything here, 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 and here is going to end up being in the M bracket N. So because of that, all that's left for the first cohomology was just everything in the off diagonal. So here, 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 here. And so this is going to give us a total dimension. Well, in each of the four quadrants, we have a dimension of n minus 1. And so the total dimension should just be 4 times n minus 1. And we can actually characterize what all the weights are going to be here. So any weight along this main diagonal of just n is going to be of the form e to the I minus e to the I plus 1, delta I minus delta I plus 1, and so on. And so all of the weights appear. Well, since we're taking the dual, we'll just multiply them all by -1. So our weights are going to be of the form ei plus 1 minus ei, delta I plus 1 minus delta I, and so on. Something similar happens in the case for Qn as well. So Qn, I don't think I defined it earlier, but it's just going to be the set of all matrices of this form, AA, BB. So all the matrices in the or the top left and the bottom right quadrants are going to be the same matrix, and the same for the top right and the bottom left. So this is just as a subalgebra of GLN. But then the same sort of principle holds in Qn as did for GLN. The derived subalgebra is just going to be, again, all of these elements in these upper right-hand corners labeled in red. And then the elements still in n mod, the n bracket n will be all representatives from the first cohomology. So this is going to end up having a dimension of 2 times n minus 1. And again, we have being characterized the weights. It'll be something in the form epsilon I plus 1 minus epsilon I. And then as for the even case, and then for the odd weights, it'll just be epsilon I plus 1 prime minus epsilon I prime. Now, for the second cohomology, this tends to get a lot trickier, and the calculations tend to get a lot more involved than they do the first cohomology. So from our classroom spectral sequence that we had just a few slides ago, we know that any cohomology Hn of n comma c needs to be isomorphic to the direct sum over all I plus j equals n of hi n mod I, comma hj IC. So in the case of the second cohomology, we can just write this as a direct sum here of the second cohomology of n mod I, comma h0, and so on. But actually, since in all of our cases we had that the matrix for the subalgebra I was abelian, this this group right here, this h0 or this h1 of IC, this ends up equaling just the super exterior product. So because it's abelian, that simplifies considerably as well. So with that in mind, I guess what I'll say what's particularly nice about how we're defining these ideals as well is that these quotients here end up being elements or isomorphic to smaller elements in the families that they correspond to. So if we go back to our ideal up here, well, here's the whole module with the whole subalgebra n. If we mod out by I, all we'd have left would be here, 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 and here. It turns out to be the case that when we quotient out by this and we're just left with this, this ends up being isomorphic to the n plus from GL to 2. So as a result, if we want to find the cohomology of our original subalgebra, by quotient out by this, we can break it down into something smaller. So going down here, using the fact that H0 is just going to be isomorphic to C, and so on. This is going to be isomorphic to, and we'll just let n sub k denote the the n from GLKK. Then H2 of NKC is going to end up being isomorphic to H2 of n sub k minus 1. And then this is just going to equal C. Direct sum H1 and k minus 1 I star. Direct sum H0 and k minus 1 super exterior 1 I star. So what this is going to enable us to do is, if we can have some base case, looking at like this cohomology group right here, this H2 of n sub k minus 1 comma C, we can compute the cohomology for origin dimensions recursively. So if we know this cohomology already, once we figure out the H1 case here and the H0 here, that'll enable us to figure out the cohomology for a higher dimensional case. So let's just start with the case where we're looking at GL22. So in GL22, the subalgebra N is going to consist of matrices of this form. So upper triangle going into the quadrant is just going to correspond to matrices with elements here, 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 here. But as it turns out, in this case, the algebra is going to end up being B. So in this case, N is a B. What that means is that any cohomology for N, so HK of N of C, is going to end up just being isomorphic to the super exterior. Super exterior okay. And then we can work out like what weights this would have to correspond to, what the dimension is, and so on. So if we're going to look at H2, this is going to be isomorphic to, well, the symmetric to on the even elements, direct sum, the even elements, tensor, and then direct sum. Oh, I'm sorry, I got that backwards. They'll be exterior on even, and then direct sum symmetric on the odd. And then we could work out that this is going to have dimension 1. We have 2 possible odd weights, 2 possible even weights, so this would have dimension 4. And then we have 2 even or 2 odd weights, and so S2 of N1 star is going to have dimension 3. So in total, H2 and C is going to have dimension 8. And then additionally, we can use this to characterize what the weights would have to be. Yeah, like I said, once we quotient out by our ideals, looking at the n sub k for higher dimensional algebras, modding out just reduces to the n corresponding to a lower dimensional algebra. And so this will enable our cohomology to be computed recursively. So essentially how I was able to figure out like what these dimension and weight formulas were. Let's just say a careful analysis of what was happening under the action of the differential. For higher dimensional ones, this actually does get kind of subtle and requires some care. So I'm going to give you a sketch of what will happen with the GL33 case. So with GL33, if we want to look at H2 of, let's say, N3C, this is going to be isomorphic to, as always, just H0 N2, lambda 2 height, super exterior, direct sum 1 and 2 of just I star, and then direct sum H2 of N2. So we've already computed what this H2 term here is. We know at least this is going to have dimension 8, and then we could have figured out what weight it corresponds to. This term right here, this is just going to correspond to fixed points under the action of N2. Fixed points of the super exterior under the action of N2. Maybe we want to just scroll back up here. It turns out that if we look at the action of N2 on I star, so corresponding to the elements here, one can show, like using the I guess just the super commutator rules and the bracket, that any fixed point of the action of G2 on the super exterior just has to be either a tensor product or a wedge product of highest weights of the original I star. Those are going to correspond to elements here, 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 and here. So the highest weights of I star are going to be of the form epsilon 3 minus epsilon 2, epsilon 3 minus delta 2, delta 3 minus delta 2, and delta 3 minus epsilon 2. So any fixed point under the action of here has to just correspond to either a wedge or a tensor of elements here. Now, these two are going to be the even ones. These two are odd. So again, just like in the computing the whole cohomology of the DL2 case, we can either take both evens and wedge them together. That corresponds to something dimension 1. We can take one even and one odd, so 2 here times 2 here, that gives us a total of 4. Or we can just take a symmetric power of the 2 odds. So in total, this is going to correspond to a dimension of 1 plus 4, which is 8. Now, this middle term right here, this H1 of N2 comma I star. This is probably the most, I guess, the most tedious one to actually compute. So again, it just involves looking at the weights and which weights can appear either in the kernel or in the image of the action of the differential on the original cochain complex for commuting the cohomology. So let me just write out again all the weights that can appear here. So the weights that will appear in N2 will be of the form epsilon 2 minus epsilon 1, delta 2 minus delta 1, I should say epsilon 2 minus delta 1, delta 2 minus epsilon 1, and delta 2 minus delta 1. And then the weights that'll appear in I star are going to be epsilon 3 minus epsilon 1, epsilon 3 minus epsilon 2, epsilon 3 minus delta 1, epsilon 3 minus delta 2. And then similarly over here, delta 3 minus epsilon 1, and so on. So if we look at the action of the differential on our original cochain complex, this is going to, again, preserve weights. So if we have just an element of some given weight in H1, well, the differential is going to send it to something of that same weight in C2. So the idea is that any weight if you look at any weight in the original C1, well, any weight in here, because this is going to be just equal to that tensor product, is just going to be the sum of one weight in N2 star and one weight in I star. This has to map to something in the superexterior raised to the second of N2 star tensor I star. And so any weight in here has to be the sum of two weights in N2 star plus a weight in I star. Well, because of that, we're just trying to essentially find all of the weights that can be expressed both as the sum of one element in N2 star and one element in I star, versus those that can be also expressed as a sum of two elements or two weights of N2 star plus one weight in I star. And then you'd also look to see which ones would correspond to just a sum of one weight in I star to figure out the image. There is a bit of I guess subtlety involved in whether or not being a sum of elements or being a weight, non-zero weight in C1 and in C2 is sufficient. It turns out that there's a bit more complication, but I don't want to get too far into that. It does require a bit of care with that. But anyway, this ends up being just a set of dimension 12. And then in total, this is just going to have dimension 8 plus 8 plus 12, dimension 28. I prepared an example for Q3 as well. I think I'm running a little short on time though, so I may just skip that. Yeah, anyway, I'd like to conclude just with a list of tables of, well, first of all the dimensions of these cohomologies for the classical cases, for the infinite families, GL, OSP, and QM. Additionally, just what their corresponding weight would be in all these cases. And then similarly, what the dimensions for all of the other two cohomologies would be as well. I have expressions for these in terms of their weight spaces as well. But yeah, like I said, these are a bit more complicated. So it'd be a little more difficult to write this all on one table here. Yeah, here are the dimensions for all of the two cohomologies as well. And yeah, I think that's everything. Thank you very much for listening.
Thank the speaker.
Yay.
Questions?
Is there any hope that you can extend this to H3?
So I think that the techniques would probably work. Like you can use that direct sum decomposition from the spectral sequence to write H3 as a sum of 3 or 4 sum ends. But at that point, I think the complicated or the calculations are going to get more and more complicated, really. So yeah, I don't know if this is the best approach to go for higher dimensions, but I think it's theoretically possible.
Okay.
Have you thought about working on any of the exceptional ones by hand?
What was it?
Have you thought about working out any of the exceptional cases by hand?
Yes. Yeah, so I do have the exceptional cases as well. Actually, they end up being a bit nicer. So like, for example, if we look at the D2. Yeah. It turns out that in each of these cases, the algebra that we're interested in, the n plus, ends up being abelian. And so again, we could just write it as the super exterior product of n plus. Yeah, so it works out pretty nicely for the exterior or for the exceptional ones.
Other questions for David? Okay, let's thank the speaker again.
Yes. And stop recording.
Oh, thank you.